Welcome back. Today we are going to look at polynomials. So first we're going to start real simple. The number of factors in a polynomial is given by the exponent. So for example, 4x squared minus 2 has two factors. They may not be real, but it does have two factors. And they could be repeats as well. The maximum number of turning points in a polynomial. So generally, when you see polynomials, they're gonna put it in some form like this to signify, n being whatever the top number is. So this is term n. That's the power. N minus 1 would be the term before that, associated with the power that's one lower, all the way down to the first leading integer, and the 1 here, it's assumed that there's also a 1 up here, but x to the 1 is just x, and then it is 0. So the max number of turning points is 1 less than the highest power in the case above n minus 1. So if the power is 12, then the maximum number of turning points we could have is 11. Imaginary factors of real functions. So it is possible to have imaginary factors even if the function is real. And then if that is true, we get this a plus bi as a factor, but it must come in a pair. So you can't just have one imaginary factor. That doesn't work. You must have its conjugate pair. And what that means is, in layman's terms, it's going to eliminate the I when everything's multiplied out. So I've given the example here using just the theory, I guess, of it, the letters. A plus bi multiplied by its conjugate, so minus bi here, would eliminate the center term. So minus abi plus abi would cancel out. And then when I is squared, it becomes negative 1. So I actually gets eliminated entirely, and we end up with a squared plus b. So long story short, make sure that if you find one imaginary solution, you also have another. The multiplicity of a polynomial function is how many times a 0 is used in a function. So, example, x cubed plus 4x squared plus 5x plus 2 can be factored into these three. X plus 1 shows up twice, and x plus 2 shows up once. So, the 0x minus 1 has a multiplicity of 2. Since this one shows up once, it has a multiplicity of 1. Polynomial synthetic division. This type of division, you're using one factor to divide. So there's other ways to do things like this division with more than that, but it gets really complex and you'd have to learn other ways of doing this. So only use it if you have a single like x to the 1 power plus or minus some integer. So for our example, we're going to do 4x squared plus 5x plus 7, and we're using this factor to divide it by, so x minus 3. We set x minus 3 equal to 0 and solve for x, so essentially we're finding the 0. And that goes on the outside here. Then we cascade down for each power of x, but we remove the x's. So this is the highest power of x, so that we take the leading integer, 4, 5, 7, and we would include the sign. They're all positive, so that's fine. Also, if you don't have them in order, so if one's missing, if we didn't have an x to the 1 here, so if we went straight from x squared to just a number, you would have to put a 0 there. So everything must have a placeholder when we're talking synthetic division. I gave this example here, so it'd be 407, not just 47. And then what you do is you add what's inside down, whatever this number is, you multiply it by the 3. So obviously when we started out there was no other number here, so 4 plus 0 is 4, then 3 times 4 is 12. 5 plus 12 is 17, 17 times 3 is 51. And 7 plus 51 is 58, and there's no more work to do. So what this did then is these all get 1 power less than the original. So this was 4x squared, so this becomes just 4x. This was 5x, so this just becomes 17. This 7 was just a number, so it didn't divide through equally. X minus 3 was not a factor. So we're left with this remainder of 58 over x minus 3. If it had been a factor, this ending term would have been 0. And then what was left over here would be either the last remaining factor or what remains to be factored. So in this case, x minus 3 was not a factor, and this is what we get if we divided it through. Another way to do division is with polynomials is to do polynomial long division. This is more versatile. So remember how I said that this synthetic division had to be x to the 1 plus or minus an integer? We can do polynomial long division with whatever we want without issue. So I'm going to do the exact same problem but using polynomial long division. Same rules apply as long division normally, except we're just going to look at these largest powers. So the largest power of x minus 3, that's just x. The largest of 4x squared plus 5x plus 7 is just going to be 4x squared. How do we get, or what do we need to multiply x by to get 4x squared? Goes up top. That would be 4x. And then just like with normal long division, you multiply down, see what you get, and subtract. Which, 4x squared minus 4x squared is 0. 5x minus a minus 12x is 17x, and then we pull the 7 down. Again, look at the highest powers only. So x and 17x, how do we get x to be 17x? We multiply by 17, multiply through, and subtract. 17 minus 17 is 0. 7 minus a minus 51 is 58. So nothing more can be done here because that power of x is greater than this one. This one doesn't have an x at all. So the remainder is 58 over x minus 3. And that's exactly what we got in synthetic division. So if you, synthetic division can be faster, but just remember that polynomial long division is more versatile in what it can be used for. In the sense that what we're dividing by doesn't just have to be x to the 1 plus or minus some number. Next we have polynomial factor theorem. Again, this is only test if you've got x plus or minus an integer, so the same rules as like synthetic division. You set the factor equal to 0 and solve for x and substitute into the function. So again, what's the 0? That's what you're plugging in. So if you plug that value in, and again, we're going to use the same problem as we used in the other two. If it equals 0, it would be a factor. If you do not get 0 as your answer, it is not a factor. So I've actually given another example down here where it is a factor. X plus 2 set equal to 0 is x minus 2. Plug negative 2 in for all the x's. We wind up with 0. So x plus 2 is a factor of x squared minus 2x plus 8. Polynomial rational root theorem. Again, we're going to use this definition of a polynomial that we talked about earlier. And the leading term cannot be 0, and the ending term cannot be 0. If a rational root exists, so if it does, it's not necessary that it does, then at least one factor of a0 divided by at least one factor of an will be a factor of the function. That terminology is weird, so we're going to go through an example of this. So we're going to ignore the signs for now. we'll make the possible answers plus minus at the end to deal with that. The factors of 4 are 1, 2, and 4. The factors of 2 are 1 and 2. So at least, if a rational root exists, one of the A0 factors, so that would be 4, divided by at least one of these factors will be a factor of the whole function. So let's do that. If we divide every possible factor of 4 by each factor of 2, so 1 over 1 is 1, 1 over 2 is 1/2, 2 over 1 is 2, 2 over 2 is 1. We already had a 1, so we don't need to put it in again. 4 over 1 is 4, and 4 over 2 is 2. We already had 2, so we don't need to do it again. So these are all the possible results we get. And as we said before, we're going to make them all plus minus. If we test these via synthetic division or polynomial division, we will eventually find that x minus 1 is a factor of 2x squared minus 15x plus 4. Or I'm sorry, we'll find that x minus 1 is a factor of 2x cubed minus 17x squared plus 19x minus 4. And that this 2x squared minus 15x plus 4 remains to be factored. In other words, x minus 1 times 2x squared minus 15x plus 4 equals our original function. So this is just a way of trying to whittle down guesses at what the factors might be if they exist. That's the point of the polynomial rational root theorem. And remember how we said this plus or minus? Well, there's a way to reduce the number of guesses even further. So in Descartes' rule of signs, we're going to ignore any missing powers of x. So that's unusual, right? When we talked about like polynomial long division or synthetic division or anything like that, we had to have placeholders. So for f of x, count the number of sign changes between each term. There are that many possible real roots for even number or less. Or an even number less. So if we look at f of x and we say, okay, the first term is positive, the second term is negative, so that counts as 1. The second term is negative, the third one is positive, so that also counts as another one, so now we're up to 2. Positive to negative is another one, so that's 3. There are 3 roots possible because it's to the power of 3, so the other 2 would be 0. Now we go on to this one. For f of negative x, count the number of sign changes between each term. So we do the same thing again. There are that many negative real roots or an even number less. So we go from here to here. There's no sign change if we multiply that all out, right? That ends up being negative, and so does this. Then we go from here to here. Both of these are negative, so there was no sign change. Again, 0. There's no sign change here, so again, 0. So there's 0 negative roots possible. So normally we've had another column to call out the negative roots, but we don't have any. Negative real roots, I should say. So the idea behind the even number less is that, remember that earlier we talked about conjugate pairs of imaginary roots. So you have to have 2 if it's a real function, so that they cancel out the i's when you multiply them together. So what we can do is we can trade 2 positive or 2 negative roots for 2 imaginaries. So remember that we found 3 positive roots here. We can take 2 of those away and move them to here. So this is another possibility. Never is there a possibility where we had negative roots. We already found that out. So this is stating that information again. And we already did our trade. So given this information, we know what kind of roots we would be looking for. So if we were looking at the function before, this one right here, from the polynomial rational root theorem, we'd know that we could ignore the possibility of there being negative real roots, and that would lower down our search. So it makes us guess more effectively. And maybe with these functions you could have just seen the answers, or maybe you're more intuitive about it, but if the function was very, very large, this could obviously become helpful in guessing where to go next. Next, we're going to look at the graph behavior of polynomials, assuming, again, this definition of a polynomial up here. When n is odd and an is positive, the graph falls to the left and rises to the right. When n is odd and an is negative, the graph rises to the left and falls to the right. So this is giving you like n behavior that you're seeing from these functions. So you can know just by a quick glance at it without actually graphing it all out and plugging in points and whatnot. So a lot of what we're looking at in polynomials is how to guess more effectively, or whittle it down so that you can deal with smaller pieces of it, or know information about it without actually calculating anything out. And then next time we'll get into, looks like areas and volumes.